So we had done one problem there. I want to do another one real quick, discrete problem. It's very similar to the one we did before, but just looking for different things, just to warm you up and remind you of what we did in the process. Again, using the problem solving technique and just applying that, because a lot of people weren't able to move that in class. So I'm going to do the same. It's a same setup, basically, two charges extended, but it's I think last time we looked for the angle, which is and then I wanted to introduce a small angle approximation, which I did. This one is a little bit more straightforward. So to give you an opportunity, again, to kind of revisit that problem and kind of measure your progress with being able to incorporate and understand how to approach a problem like that. Also, the other thing is that it utilized both, it was a comprehensive problem in that we had to use concepts from last semester, Newton's laws, this is a really nice example of the way that looks as we move forward. And, Newton's law is laws of motion are always applicable. So that's something that you have to do. So we have a problem where we have these two charges suspended and extended on wires, and have a repulsive force, repulsive force. And so whereas last time I didn't give you the angle and we figured it out, this time we'll know the angle. And I'm going to ask for some other specific quantities associated with this motion, with this static problem. Cool. So let's make it doesn't matter. So two particles suspended at 35 degrees to the vertical. Strings L equals 30.35 centimeters. It's a mess. Why don't we make them protons again? Oh no, I wasn't with charges, so not protons. So let's take a mass. Yeah. So two particles. Suspended at 35 degrees. With strings of length L equals 25 centimeters. Let's say the masses are 0.15 grams. And let's see, so the the same as the chart, but I have different charges, so this will be Q1, Q2. Masses, if the masses are and Q1 equals 420 nanocoulombs. Determine the charge of determine Q2. That'll be one question. And the second question will be determine the value of the of the field at the position of charge 2. In fact, let's make it E2 or something. E2 at point 2.
Stop.
So, two particles, charged particles suspended at 35 degrees with strings of length 25 centimeters. This is L, both of them, and theta there as well. And the masses are 0.15 kilograms, 0.15 grams, and so not even 1 gram. And so find the charge on this guy, if this guy is 420 nanocoulombs, and find the electric field at the point where charge 2 exists. Now remember those properties associated with fields, that you can have a field at a point even if a charge is not there. Now I encourage you, remember the steps of the problem solving technique. Explicit and implicit information, sketch and diagram, which is going to incorporate identifying all the forces, finding components of the forces in step 4 if you need to. And then in step 5, first down, write down all the possible physical constants that apply. Of course, Newton's law, laws of motion apply. In this case, decide whether it's the first law or the second law. Third law always applies. Right? And do a free body diagram. Also look at, Coulomb's law applies, definition of electric field applies. So basically 3 concepts. Then I would just write out all the equations, the general equations associated with those. And then in this case, you're technically only dealing with 1 particle, even though you have 2. So the specific and general equations will be about the same. And then evaluate the knowns and unknowns and figure out your mathematical path to the problem. Oh, I guess I should give you, couldn't do that. No, yeah, cool. So work on that for a few minutes. I'm gonna see. Thank you for helping me lead me through that.
Lucky.
All right. Make sure you're moving through this well. So explicit and implicit information. I don't know, things are pretty straightforward here. Theta is 35.0 degrees. L is 25.0 centimeters. And, well, one thing is implicit. Since I, you know, I said both the masses of both balls are the same. So M1 equals M2 equals M equals 0.150 grams. Kind of imply that Q1 equals 420.0 nanocoulomb. One thing is that you might say, train of thought. Yeah. Oh, yeah. It's going to make a note about the significant digits. We've got. Excuse me. Our answer will only be significant to 3 significant digits in this case. So that's something to note. And we're looking for Q2 and E at the point of 2. So E2 or something like that. So that's steps 1, 2, 3. Sketch and diagram. So this is a sketch. You don't have to do that. The diagram is, again, the first thing is to choose your origin. Generally speaking, we'll place that at the point where we're trying to find the evaluate forces. So I'm going to put it at the center of mass of charge 2. So axis will look something like that. And this guy here. And then I generally like to draw the forces on that diagram, and then I'll go to a free body diagram to evaluate a little bit further. But we've got 3 forces. We've got gravity, of course. mg is straight down. We've got a tension force along the direction of strain. And we've got the Coulomb force. Oh, that's the other thing I've kind of implied. I didn't tell you, I guess I didn't. Yeah. Well, yeah, I made this positive, even though I didn't explicitly say that. So if it's positive, then that implies that charge 2 is also positive because they're spread apart. Otherwise, charge 2 would be negative. So that's implicit information. And that's important because that tells you what direction the force must be in, the Coulomb force on the particle. So yeah, it's true. I could have just given the magnitude here. Sometimes I do that. I should have been probably more explicit. But in the case where I don't, obviously, you assume that the charge is positive. So yeah. So that means that it's a repulsive force because clearly the balls are being repulsed, which means that you know implicitly that the Coulomb force is in the direction along the positive x-axis based on the way you set up your coordinate system. So that's steps 1 through 4. So as I mentioned to you before, at this point, what I would encourage is you just write down. So that it helps write down the concepts applicable. It helps to be able to learn the lexicon. It reinforces what you know, what you don't know. And it's actually a jumping off place for being able to, if you get the problem and go through it really well and don't make any mistakes, that's cool. But if you do make mistakes, then the first thing that you want to question is if you have applied all the physical concepts to a problem. And so the more you begin to identify that before you start, it kind of places it as a seed in your mind, just in case something goes wrong and you have to kind of cycle back and look for errors. So all of the possible physical things that, directly apply, I guess would say, is certainly Newton's laws. In fact, specifically Newton's first law, because it's a statics problem, no acceleration, not the second law. And again, the third law always applies. So that's because forces always occur in pairs. So anytime you have a force there, there's the third law applies. But it's not really directly applicable to this problem, other than the fact that you've identified there's forces. And, you know, so when I ask that question, or when I'm thinking about that, that's one thing to understand, that the third law, if there's a force, third law always applies. Doesn't really give you any quantitative thing to work through unless it's asking something about the other charge. So really, when I'm asking and thinking about that problem, it's really the first law, the second law, specifically that we're trying. So it's Newton's first law. Coulomb's law. Right? I guess technically for the second question, it's also the electric field associated with a point charge, which is technically not Coulomb's law. So E field of a point charge. And finally, the definition of the electric field. Definition of the electric field. So 4 concepts actually. Now, if you kind of briefly write down what those equations associated with those are, all right? So Newton's first law, obviously, net force equals 0. Coulomb's law, a couple versions, but in this case, net electric force equals K sub B Q1 Q2 over R squared, where R is the distance between them. The definition of electric field is that the net force on the electric field on a particle is equal to force, electric force divided by the charge associated with that particle. Finally, this last one, E field of a point charge. The E field of a point charge is that the net electric force on a charge is equal to K sub B Q over R squared. So Q is the charge setting. In this case, I guess it would be Q1, right? Because that's the other thing about the definition of the electric field, is that when you're finding the electric field at a point, for example, we're finding it at point 2, that charge cannot contribute to the point, to the field at that point. It never does. That's one of the properties of the electric field of the point charge. A couple of reasons for it, but one way, just specifically mathematically, like this R value here is the distance that you are away from the charge. But in this case, if you're trying to find the point at the charge with the field at the point where the charge exists, well, it exists at, you know, it's 0 distance from itself. So you would have to be putting in 0 in the denominator to figure out the contribution of this charge gives. So, you know, that obviously, even from a mathematical point of view, that value is of E is not defined for that. So the value of the electric field at this point is due to the field associated with this charge. And so that R distance is going to be the distance that you are away from that point we're trying to find the field. So it's this total distance here, which you can work out through geometry. So, you know, everything is there. So once you, so that's basically steps, you know, up through step 5. Step 6 is to now go through and specifically write those equations to this guy. Well, you still got to work out the free body diagram over here, so I would do that. Let me put up the free body diagram over here. PP should probably have done that already before going to step 5, but whatever. So this angle theta is this angle theta here. So I'm just going to do it in my head and write it down. And I'll let you go through that. So make it green. So that's theta. This is theta. So you're going to have cosine on the positive y and sine on the negative x. So over here, this is going to look like this. Up, you're going to have t cosine of theta. In this direction, you're going to have fe, but it's the Coulomb version of it, so it's this guy, right? I'll just write that in, fe. Over here, you're going to have t sine of theta, and straight down, you're going to have mg, mg. So that's what your free body diagram is going to look like. So you can start by finding the sum of the forces in both the x and y directions, and then moving from there to figure out, you know, what your unknowns are. So go ahead and work through that. See if you can make some progress and get some final answers there. Any questions about that? About how I've set that up? So that's considered a straightforward problem. I wouldn't even really at this point consider that an intermediate problem. It's more like basically just a standard problem in between easy and difficult. It's the basic thing that you expect them to be able to work through, incorporating concepts into every. I mean, maybe it's, I don't know. It's all relative, right? If 2 + 2 is difficult before you know how to do it. You know how to do it. But the point that I like, I'm kind of reinforcing these types of problems is because, it's the process of putting different concepts together, right? And being able to show that we have a solid problem-solving technique. That's the thing at this point in your 3 semesters you want to start to really feel comfortable with. Yeah. All right. So work together, kid. All right. Let's go ahead and knock this out. So I always like to get the analytical solution first. So, and then put in the numbers. Clearly keeps the mathematics clear, the path through the problem clear. So I guess we do what I said. We start with Newton's laws. So I'm just going to keep the numbering of these equations. So say that the net force in the y direction is equal to 0, of course, the first law. In the y direction, we have two forces. T cosine theta minus mg equals 0. So that leads to, I guess, kind of our realization that you can say something like solve for t. So t equals mg cosine theta. I'm going to box that in. I didn't ask for the tension in the rope. That's I could have, obviously, I could have done that, but we'll just use it as a preliminary result. You would have to do that in order to get what I've asked. So this is more of a situation where I've asked questions that I'm not leading you through. In the y direction, we have, again, the first law. So net force, so no, in the x direction, I guess, in the x direction equals 0. Just did the y direction. So I have Fe equals Fe minus t sine theta equals 0. Now, you notice you're looking for the charge, and at this point, no quantity of charge has come in, but at this point, you would see, okay, well, the force on that is Coulomb's law, and Coulomb's law is this. So at this point, you would incorporate Coulomb's law into that problem. So, I mean, talking about the unknowns, sticking specifically to the problem-solving technique, there's only one unknown in this equation, which implies why you would solve for it. Here, I've got a couple. I've got Fe and I've got T. Well, I need at least one more equation. Where do I get, the other equation from? It's not this guy. Well, I mean, I guess actually you could. So there's a couple things here, right? Since I know I could solve for there's a couple ways I could get Fe. One is, well, actually, I don't know if that's true, do I? Did I do this right? Oh, yeah, because the Q is out there. Right. Yeah. I guess, yeah. Okay, so you could get the value of Fe, but I'm not asking for that. So that's one way to get Fe is you can substitute this guy in here and get Fe, but I'm asking for Q. So you have to keep moving. And you realize that the Q is embedded inside that. So now I would substitute equation 2 into equation 9. And here I'm going to get that K to be Q1, Q2 equals R squared. I'm going to go ahead and take the T sine theta over. So that equals T sine theta. So at this point, a couple of unknowns. I've got 1, 2, and 3 unknowns. Well, I've solved for T here. So at this point, I probably would go ahead and substitute T into 7 into 10. So equation 7 into 10, that's going to give me K sub B, Q1, Q2 over R squared equals, so mg sine over cosine is the same as, so tangent. So basically mg tangent theta. That's what I'm going to get there. And I'll substitute that in. So that reduces, I get rid of that unknown, T, but I still got 2 left, R and Q. Q2, the thing I'm looking for. Now, normally in step, 5, I just usually write down physics concepts. Because that's what I just let the mathematics kind of play out. But there's also geometrical concepts associated with this guy. And R really is this distance here, as we mentioned before, and I don't know that, but I can use geometry to figure it out. So this distance here is R, the total distance, end to end. Have the base here, so come over here. From geometry, I've got a right triangle here. So if this distance is L, then this distance here is L sine theta. It's opposite from theta. So R is twice that distance, so I can write a little equation here just so that R is equal to 2L sine theta. It's from geometry. So that handles R. I can go ahead and stick that in. R squared is going to be 4L squared sine squared theta. So go ahead and put that in. So substituting 12 into 11, we get that K sub E, Q1, Q2 over, is that 4L squared sine squared theta equals mg tangent theta. And you see we're home free. There's only one unknown now, and that's Q2, the thing I'm looking for. So I have to solve, do all the algebra and solve all that mess for Q2. So let's do it. So I'm going to have Q2. Let's see if I can do this in one fell swoop. Cross multiplying, this thing is still going to be able to. So I'm going to have 4L squared sine squared theta divided by K sub B Q1 times mg tangent theta. Now technically I'm done, but I'm going to go ahead and simplify some things here. I think it's worthwhile doing that. Now remember that K sub B is what is it? 1 over 4 pi epsilon naught. That's the definition of K sub B, right? K sub B Coulomb constant is defined as 1 over 4 pi epsilon naught. Yes, you could. I have the answer. Yeah. Well, I guess you. Yeah. I mean, maybe that's cool. Maybe we could leave it like that. I probably would break it down, the tangent thing down again. Yeah, maybe we could do that. So I probably would just leave the case of being like that. Let's do that. So it's a bit more transparent. And the final answer, I guess, I would write as, so sine, this is sine over cosine, so that's sine cubed over cosine. So maybe we could put all the constants and stuff together, how we want to do this. So we're going to do Q2. Q2 equals 4L squared mg over K sub B Q1 times sine cube theta over cosine theta. Yeah, I think that's what I will leave it. So just let's be complete. I'm curious to see how much charge that will be. So let's put in the numbers as well. Now, Right. Now we didn't even, so to get E, we actually didn't have to finish all of that. We could have gotten E directly from equation 9, right? Because to get E, we're using the definition of E, which is this guy. So since we, from equation 7, well, yeah, let's go ahead and do that, then I'll put in the numbers. So let me just go here. Keep some of that stuff up there. Basically, back from equation 9, so from 9, we could solve for, essentially, this is Q1, right? Is it Q2 or Q? Oh, maybe we did, because that's, actually, we did have to solve it, right? Because this is actually Q2, right? It's the electric field at that point is the force on that charge divided by the value of that charge. So my bad. We actually did have to figure out Q2 in order to go back and get FE. My bad. If we wanted to know the field at this point, though, we wouldn't have to, we could just plug it right in. We could use equation 9 because we know what Q1 is, and which, oh, but that's a different force on it. Well, actually, yeah. Oh, that's actually a good problem. I never thought about that. Let's, I'll do that in the end. That's something I could have asked. And that's a really nice thing, because that way you actually would have to use Newton's third law to acknowledge it in order to see that. Yeah, so let's do that as a number 3. I'll go back and explain what if I wanted to find the electric field at that point to show that they're not necessarily the same. In fact, they won't be, in this case, the same field, even though the force will be the same force because of the third law. That's a good thing to point out. So yeah, so let's go ahead and get this charge, and then once you get that charge, then you have to realize in order to get the field at that point, then you have to use this law, the definition of the electric field. And so the unknown in that case, basically the two unknowns are Q2 and FE, but now that I know Q2, I have to get FE, but I can get FE from equation 9. That, so from 9, you see that FE is equal to basically T sine theta. But if T is equal to mg cosine theta, then FE is equal to T is equal to mg times the tangent of theta. So then I would plug 16 and 15 into 3. Now, yeah, I guess if we want to do it analytically, sure, why not? Let's go ahead and do that. To get them all in base. I mean, you could get the value of that and plug it in, but to get, you know, maybe I didn't ask you for Q2. Maybe the only thing I asked you for is FE, and so then getting the analytical solution first to show that, then it would be this. It would be the final solution for FE. So basically, when I put that in, I guess I could see it from here. I'm going to have, I'm going to be dividing by this thing by Q2. So from this format, you see that basically the mg tangent theta is going to divide out. And so, yeah, the mg tangent theta is going to divide out. So when I stick this thing, when I divide FE, mg tangent theta, by Q2, which is all of this, then in the end, my FE, my E at position 2, is going to be equal to K sub E over Q1 divided by 4L squared sine squared theta.
Professor, real quickly, how is T sine theta equal to mg tan theta? Since
It's here, so from here, Fe is equal to E minus is, Fe is equal to minus T sine theta, right? So, because this is Fe.
okay,
You see that? You see that?
yeah,
Okay, and so T, I take T and plug that in there, and T is going to be mg tan. So basically, it's from here. Basically,
okay,
it's equation
yeah,
11, but I just written equation 11 as Fe. Got that?
yeah, got it.
You got that?
Yep.
Hello? Yeah. And before I find the numbers, I guess you're already working on that, but I'll just go ahead and work on, so the third problem thing I just thought about. What if I wanted to find the electric field at point 2, at point 1? Well, symmetry is one of the themes of the courses. Because I've made the effort to find these, the analytical solutions, even though these charges aren't the same, basically the physics is symmetrical, right? Like if I were to go back and work through all of this, it's just going to look like this guy. Sure, it's like, in other words, if I were to go around the other side of the board and look at this charge from the other side, then that's how the forces would look, the directions of the forces, even though they're different values, on this guy. The tension of the string, I guess, would be the same, but and Fe would be the same, but Mg would be different, sure. But the charge is different. So, like basically all the physics is the same. So if I have the general solution here, you could probably just use that solution to write down what Fe is there. And you see that the angles, everything is going to be the same. Like Ke is a constant, 4 is, obviously L hasn't changed. The angle is the same, right? So by symmetry, you could just write down that the value of the field at E1 is just going to be whatever is different. And the only difference is that the field Q1 can't contribute to the field at this point. And you realize that field at position 1 is associated with the charge at position 2. So E1 should, by symmetry, you could just write down, in this case, it'd be Q2 for L squared sine squared theta. So just by looking at the analytical solution, you can clearly see that the electric fields of the 2 points are going to be different, which they should be. And one other thing, though, is that here you would have to actually explicitly kind of use the third law, Newton's third law, right? That even though the masses in this case are the same, I made them the same, but even if they weren't, the charge certainly is not the same. By the third law, this Fe is a force on charge 2 due to charge 1. So the same magnitude of the force has to be on charge 1, but in opposite direction. So that's also Fe. So that's something where you would have to explicitly use the third law. Otherwise, you couldn't do the problem because you wouldn't know what the value of Fe of the force. I mean, I guess if you redid the thing over again, you could do it from Coulomb's law point of view. But you don't have to do that. You could just use the third law. So that's a really nice, comprehensive problem, showing possibility of these things. I'm curious about the number. Go get my calculator. All right, yeah. So just click out the number on this one thing. All right, so yeah, so to convert the 25 to 2.25, I guess. So we have 4.25 squared, and the mass is so that's 0.15 times 10 to the negative 3 kilograms. Be careful on that. Then divided by charge is 420 times 10 to the negative 9. Finally, we've got 35 degrees, square it, cube, cube it, 10 times. And now cosine 35. Cosine. Okay. So it's about 1,000 times less. Well, yeah, smaller charge. So I get like 15.4 picocoulombs, 1.53 times 1.54 times 10 to the negative 11. So I can shift that around to 1.5 increase. So I get that Q2 is 15.4 picocoulombs. That's 10 to the negative 12. Did anyone else get that? Someone, at least one more. Baba, what'd you say? Who said that?
I was still calculating. Sorry.
Okay. So I'll try that one more time. Let's take Oh, did I forget 9.81? I did. I think I forgot to multiply by 9.81. So maybe not. So 9.81. I did forget that. Q1 is 426. So, sorry. Sorry about that. Yeah, it's going to change it. So it puts on the same order of magnitude. So 22.4 nanocoulombs. I forgot to do, yeah, I forgot to multiply by the G here. So 22.4 nanocoulombs, 10 to the negative 9. Third time's the charm. Four. Yeah. So I got this again. So I think that's probably right. 22.4 nanocoulombs. Interesting. Now, we can stick that in here to get the value of the field. Get those numerical values as well. So E2, and we can do E1. Get those. So store. All right, so just using this equation here, get E, so 8, 9, 9 times 5. I think that's a reasonable feel. It's like, so 3 significant digits, I would say. So I get 2453.22. So rounding off, it's like 2,450 newtons per coulomb. So this is 2450 coulomb. And that is a reasonable field that you can see in the lab. And for the other guy, I just stick charge F2 in it before 20 nanocoulombs. So for each E1, 420. So well, maybe I didn't square that thing. Because it jumps up quite a bit. Maybe that's the difference. So that field is 1,000 times. Well, I guess that's right because that isn't. It's only 10. Oh, it's 10 times larger. That's right. Because that charge is 10 times. It's approximately 10 times large. It's an order of magnitude larger. Because that's 420 nanocoulombs. It's just 22 nanocoulombs. So this field I get to be an order of magnitude larger. Plus some change, double B. Yeah, so that's probably about right. So this guy is 45,900 newton coulomb. So it's like 1,000 times larger times 2, or 2,000 times larger. So that's probably right. So that kind of just reevaluating the numbers and see if it makes sense, you know, that kind of thing. You kind of want to do that all the time, not just in physics, but in science in general. Just want to write down a number and move on and think about the sensibility of the magnitude. That's a 0, 0. So I think that's probably about right because, yeah. Let's see how the charge though. Let's see how the charge. Let's see what the field. Oh, I got them switched. I got them switched. That's what's wrong. Right? Yeah, I switched the numbers in my thing. My bad. This guy it's flipped. This is actually E2. Yeah, because the field's got to be bigger. Sorry. This is E2, and this is E1. So I had a dyslexic moment. Right? Because that E1 is, wait, no, what? Just confused myself. So, okay, so first what we're doing, I was finding the field at position 2. Field at position 2 is due to charge 1. But what I put in my calculator was charge 2. So I'll keep those things the same and just flip these numbers around. Let me just do this again to make sure. I'm pretty sure that's what I did because the field at this point can't be larger than over here because this charge is smaller than this one. So yeah, it's pretty sure that's what I did. So again, for this guy, you got to use the Q1. I use Q2, I'm pretty sure. But that's a 420 nanocoulomb. So 420, yeah, times so 8 and 4.25 squared divided by and 35 sine squared divided. Yeah, my bad. Yeah, so it's just, here's where I change them here. So this is E2, and this is E1. That's it. So that I'm sure of. Questions, problems, troubles, gripes. All right, how many people, let's see, get some feedback here. So it's a slow Monday, so I gotta keep on responding, except for about Tuesday. Daniel
Yeah.
Roca, how you doing this morning?
Good, Professor. I keep trying to calculate Q2,
Yeah.
but I don't know. For me, like, it's just not working. It's just not working out. I'm still trying.
Okay. Gotcha. So this is the deal with these. So this is one reason why I work through the details. You got to practice this stuff, right? Like getting through the physics is one thing, because I remember like whenever I would do this, was first learning, I was getting the answer, but somehow I just didn't. I would always make some mistakes in here. You got to practice. Using. I know it seems kind of simple, just plugging numbers into a calculator, but I find that I had to practice it. And so you might not believe this. I don't like what I'm using is this is a digital calculator, right? This is with this calculator, I don't know where my let me see. That calculator is an updated version of a calculator I bought when I was a junior in college. I was a junior in college in 1984. It's this calculator right here. It's an HP. It's called HP 15C. So before iPhones, this HP had some of the best technology around back in the 80s. And this was cutting edge technology. This calculator I bought 35 years ago, or whatever it was. And it's never broken down. I have probably changed the batteries in this thing maybe 6 times in 35 years. That's how good this calculator is. So before that, I was using like the Texas Instruments. I think now you have TI-35 or whatever. Back then it was earlier versions. And I didn't really, I don't know, somehow I just couldn't operate the thing very well. Maybe it's the difference between Apple and PC, right? I'm more of an Apple person than PC, right? But I was always making mistakes with those TIs. And so someone told me about HP, which has something called reverse logic. And so I decided to try it, and it made all the difference. And it's it's one of the first programmable calculators, just a lot of things you could do with it. And the fact that I have not bought a different calculator since in 30, but tells you like that, for me, that makes a difference. And I found that a lot of the careless errors and things that I made on tests significantly decreased. Now I still had to practice, make sure I knew how to use the instrument, but it's important. It's like a tool. It's like, you see these movies about like the Apollo program and everything, and people are walking around with slide rules, right? It's like you have to become familiar with your instrument. It's the tool that you're going to be able to use to negotiate that, because the worst thing that you want to do is to understand the physics very well, be able to go through a problem, get the right answer, solution, and then somehow you're making careless errors every time you calculate the value. That you don't want to do. It's just the most frustrating thing. So I was saying about the calculators, ultimately, they made digital versions of the same calculator. And so literally I've been using the same calculator for 35 years, right? And so I'm very familiar with it. And so I make less careless errors other than things like what I just did there, but no numerical errors, usually not, or less, much less. So you want to be able to practice that. Practice where you're storing your register, your numbers, all that you should have to kind of, have that down, so that down pat, so that you don't have to worry about being able to suss through negotiating a device while you're trying to calculate. So I'm pretty sure these numbers are correct. So you want to practice it until you do it. Now, the other thing that I normally do if I'm on a test, I won't do it the way I just did that here. That's probably show you the mistake that I made. Like when I'm calculating the numbers, I'm going to write out all the numbers here first, put all the numbers in that equation, and then calculate it from there, so I don't have to kind of do that in my head, because I will make mistakes like I just did, mixing the two fields up. Then once you do that, then, and again, one of the most difficult things is if you make a numerical error down there and you figure out that it's not right, and you didn't go through the steps, like at least the way that I'm doing this physics, I can tell whether a mistake is more likely a numerical error or whether it's a physics error. That's hugely important. And one of the reasons I can do that is because I have gone through my problem solving technique. So if I get a wrong answer down there, I'm immediately going to go back and, I can, if it's a numerical answer, then I can find it in the way that I just showed you. If I suspect that it's a physics problem, physics error, then I have all my equations enumerated. Everything is worked out. I have my different sections. Usually, sometimes if it's a complex problem, I'll actually have one of those problem-solving templates that I gave you and actually do the problem on there, so it's easy to go back and check different sections. But even if I don't, like I've done that so many times in my head that I can go to different sections and I know where I am, and I can check units, I can check physics, I can check all these little things to find errors. And that's important because I'm following the same process every time to be able to go back and troubleshoot. So I would suggest, again, in your case, you shouldn't have a physics error because I've told you what the answers are and worked it out for you. But still, you can see, I think you can see hopefully how advantageous having a technique and a process can be whenever it's more important when you make a mistake and you have to go back and troubleshoot. So, yeah.
Professor, I was finally able to work it out. I got the same answer. I got the same answer now.
Good. Well, what mistake were you making? Do you know?
I think where I messed up was when I was plugging in the sine cube theta into my calculator. I guess I got a little lazy, and instead of putting sine, because I did a sine 35 degrees to the power of 3. And so this time, instead of doing that, I wrote them all out. I put sine 35 times sine 35 times sine 35, and now I got the answer.
Okay, that's a good example of what I'm trying to say. Now, it's good you found the mistake, but if you're working under pressure on a test, you don't want to have to, you want to be able to use the calculator, more efficiently. And so somehow you don't know how to put in the exponents right. Maybe usually, are you using a TI, a Texas Instrument?
Yeah, I'm using a Texas Instrument.
Yeah, so one of the things with TIs that I don't like is that you have to force it so much that you have to put in the parentheses. So like if you did sine theta to the third power, who knows, it might have interpreted that as maybe just cubing the angle, not the sine. I don't know.
Yeah, that's what I was thinking. It can get a little tricky, but like I said, it's just a matter of practicing that. Because I think that was probably my issue, just learning where to put the exponent, because it is a lot of parentheses and it's easy to mix up.
Yeah. So, just for future reference, I don't know if you know about HP technology, but this reverse logic thing that I'm telling you about, it alleviates having to do that. It's a little bit, there is some little work to learning it, but with HP calculators, they use something, it's called reverse logic or something logic, where you can put it in, you kind of put it in like a computer. And it takes, as I said, it might take, some time, maybe a week or so, I don't know, to get it comfortable with that, because it's kind of, different thinking than the way you think about calculating normally. But you don't have to put in parentheses. And you see how fast I did. Like I did the thing 3 times before you all, some of you probably did it once. It's not just because I'm better. It's also because I'm using a calculator where I don't have to worry about all that stuff with Texas Instruments. And HP calculators, I think they patented. They're the only ones that use that kind of logic. You can maybe Google it and read what I'm talking about. It's worth probably doing. Whatever. So just for your information.
Another question I have, Professor, is because like at least in my answer, when I plugged in the value for L, I converted it into meters. I didn't leave it like as centimeters. So I did 0.25 times 0.25. Like, would that have been the correct way to do it, or should I have left it as a 25?
Oh, no. That's, I'm assuming everybody knows that now. No, we have to, everything has got to be in, so you're right. Yeah, you have to convert it. Everything has to be in System International, which is MKS, meters, kilograms, seconds. So this, you got to convert to kilograms. This guy, you got to convert to meters. Everything, this converts to coulombs.
Yeah,
like everything has to be converted. And I didn't say anything about that because I'm assuming by now everybody knows that. But yeah, you have to convert everything. That's true.
All right, for sure. Yeah, because
Yeah.
All right. I think because I did that, but if anything, I probably forgot to convert the grams into kilograms. So I'll make note of that. That was just a little minus error.
Yeah. Okay. Yeah. Yep. Anything else?
Just so I understand a little better, difference in calculating E1 from E2. L is the same and Q is the same. Correct? I'm sorry. The only difference is the charge. The reference distance is the same.
Yeah, the only difference is the charge. So this should be, I didn't put that back. The only difference is the charge, yeah. What else? What'd you say now? Okay. I'm sorry, ask the question again, Baba Tunde.
I'm just saying, calculating, I guess E2 is referring to the electric field at charge 2. And
yes.
E is referring to the electric field at charge 1.
Yes, E1 is, yes.
Okay. I just wanted to make sure that distance that we're accounting for there, I guess because of the fact that it is represented as 4L squared, means that we don't have to worry about the distance from the charges to each other. We're only worried about the point of attachment.
We do have to worry about it. It's this distance here. It's always, the equation is Coulomb's law. So the field, the value of the field is, I mean, you could compute that a couple different ways. Let's come at it from a different point of view to answer that question better. It is there, but because we approached it from a different point of view, we had already worked it out. So I approached it from the definition of E, right? But you could also calculate it directly now that you know the value of each charge this way. E is equal to K sub E, Q over R squared. Well, the K sub BQ is on each, is in the numerator. But the R squared is the distance from the field point to the charge. But for each one, that's the same distance. So the E2 here is the distance, that E2 is due to Q1. And the distance between that point and Q1 is R.
Okay.
The field here is E1 due to charge 2, and the distance between that field point and that charge is R.
All right, so it's represented as E2 equals to KQ, E2 goes to KQ1 over R squared.
Yeah.
Got it, okay, all right.
And so when you put that in, so E2 is KQ1, right? But R squared is, R is L sine theta, so R squared is 4L. So if you put that in, you got K sub B Q1 over 4 L squared sine squared theta, which is what we got here, or here.
Okay.
But we came at it from a different point of view just because we were already working through the problem. We didn't have to use the electric field for a point charge because we had figured out what the force was on that charge. So I used, I used the definition of the electric field that E2 is equal to the force on 2 divided by the charge divided by charge 2. And when we put all that stuff in, working that, and charge 2 was over here and whatever, then it came out to that formula. So you can see, like, it's really doing it from using different physics concepts. This way we use Newton's law in the definition of the electric field, mainly because we didn't know what Q2 was. In order to do, the definition of electric field, we would have had to, well, I guess we didn't have to do that to figure out the field there, because we already knew Q1. But to do the field over here, we would have. So we could have actually, you could have actually figured out what the field is at E2 without actually having, is that true? No, that's still not true, because we would have had to know what the force is. And so in order to get the force on that charge, we had to figure out what the value of that charge was. So we still would have had to work it out. But anyway, there's two different ways you can approach. You can get it from E directly by going to the electric field of the point charge, or you could go the route that we initially did. Either way, the answer to your question is the same. You still have to know the distance, because both Coulomb's law for force and the electric field of a point charge are based on the distance that you are away from, in the first case, another charge. In the second case, how far the field point is away from specific charge setting up the field. So you still would have to know that distance.
Thank you.
Yep. So I guess we passed the break in the time. It's only 8 minutes past the break. So let's go ahead and take a break right now. And when we come back, so this is, I guess, chapter 5-ish. I guess we're pretty much, so we're done with kind of, I guess, the basic stuff. So from the next part of the chapter is the final stuff is we need to look at figuring out the electric field based on continuous charge distributions. And that just becomes kind of a straight up math problem where we're doing integration. So I usually leave that for a whole section once we've kind of gone through and understand Coulomb's law and the electric field and all that. And then we can, now that we understand what it is and how to calculate it from kind of a basic point of view, then we can look at essentially more complex charge distributions. And that becomes more of a mathematical thing, is being able to set up the integral and work out the integral, and, so on and so forth. So that's what we'll focus on when we come back. I'll start with basic problems, basic charge distributions, a line of charge. And actually, we're going to start with a dipole, and then from there, figure out the electric field of the dipole. And then that is helpful, because then we'll turn it into a continuous charge distribution, look at the differences. So any questions before we leave this? Go to break. All righty then. I want to, we're going to ultimately get to integration and continuous charge distribution, and figuring out the electric field due to a line of charge, infinite line of charge, or a finite line of charge, continuous line of charge. But a nice precursor to integration problems is looking at the electric field of a dipole along what's called a bisector of the dipole. A bisector is simply a line that goes through the center of the dipole. Well, goes through the center of, seems like a line through the center of a dipole. So let me show you. But there's symmetry involved, and it's nice because it's symmetry that actually mimics the symmetry of a continuous charge distribution. So it's nice to kind of begin to think along those terms before. So we've got a lot of the kind of physics intuitively figured out, and then we can focus on the mathematics associated with continuous charge. So also it allows us to kind of set up looking at it from a three-dimensional point of view, which we kind of have to do, or it's useful to do when we're thinking about continuous charge distributions, because they're three-dimensional figures usually, or two-dimensional representations of three-dimensional figures. So here we're going to start to think about charge distributions in a three-dimensional coordinate system like so. And I'm going to make the z-axis the vertical. That means this has to be x and this has to be y. The right-hand rule, x cross y gives you z up. And we're going to set up the dipole. Remember, a dipole is specifically two charges of the same magnitude but equal but opposite polarity. We'll set it up so that the origin, we'll make the dipole on the z-axis. It's a bit of a setup here, so I need to have that there where I can see the thing. So I'm going to make the positive charge up here on the z-axis and the negative charge below, equal distance below, something like this. And I'm setting it up symmetrically so that the distance, basically the distance of the dipole, I'm going to make 2a, where, the positive charge is at plus a and the negative charge is at negative a. Do it like that. So I represent, like, when I go from basically the x-axis to that position. So that position is A, and then the same distance below here is A. Sure, I'll go ahead and put it in. Why not? So I have to kind of draw it three-dimensionally so that we'll kind of give that impression still. So something like that. Hope that helps your perspective a little bit. So I guess if you saw this problem in words, it would be like, so let's have a field point over here, field point P. So the thing, so that's field point P. So the problem might be, determine the electric field at field point P due to the determine the electric field at point P along a bisector of dipole, a distance, x away from the center or something like that. So I guess if it's along y, so that distance right there would actually be y, right? That would actually be the coordinate y position y, and y is a specific value. I could make a d or something like that, but we're going to have the answer in terms of y, right? So y is just a variable. It's not a variable for this. It's a particular value for this point, so it's a known. But I could make it any position y, so that's why we generally conventionally still keep it as a kind of a variable, even though it's a constant for this particular problem. So that's a specific distance, a y, away from the center of the dipole along the bisector of the dipole, which is, I've set it up so that the y-axis is the bisector, that is the line that goes through the center of the dipole. So determine E, and the way we write this is like, would be like E of P, determine the electric field at P, a distance y, along the bisector, a distance y from the origin. Along a bisector of the dipole. Yeah. All right. Well, technically, we are still using Coulomb's law for this problem, right? The electric field at this point here is going to be due to the electric field of these two charges. Now, remember, we could draw the field lines coming out, radial and inward here, but remember, I told you, once you understand what the field is coming from, you can just go directly to figuring out and drawing the field line that passes through that point associated with each charge. And so the field line at point P associated with the positive charge, you got to point radially away from the positive charge. So E1 along that line, that point is going to be doing something like this. You know, it's going to be in that direction. E2 is going to be a attractive force, attractive, not a force, but field. Well, it would, the force on a test charge there would be attractive. And the field would be pointing then same, and by symmetry, you know, you might intuit that because it's the same distance below, the angle that it ultimately makes with the vertical is going to be the same magnitude, but back in the opposite direction. So 5, something like that. Yeah. So this guy's going to do something like, whatever. Yeah, a bit off or whatever. Like that. Yeah. That's E2. So the field at that point is going to be the superposition of those two fields. And you can see by symmetry, you can kind of work out a lot of things, like the Y field is going to cancel out, right? So it's going to be like E1Y. This guy over here is going to be E2Y. And those are going to cancel. What we'll add are going to be the Z fields along those directions. Now, because I have these dipoles along the Z-axis in the field point is along the y-axis, then I'm not going to have an x component. But be careful. I could have set it up so that the field point was out, like here in the plane somewhere, in which case I would have x components in that case. I'd have basically y components and x components in that case. But here I'm just going to ultimately have y components, z components. Sorry, I would have, yeah, I guess you might even have, if I'm out there, yeah, I guess I would have x and y components and z components. Do it the same way, just a bit more mathematical and hard to see, so we just normally set it up like this. Besides, I want to get onto the integral problem anyway. So, yeah. So then here, this field would be, you know, I'm going to have both the two components really. They would be the same magnitude and equal, and obviously the same direction. But that's, you know, I would have basically superimposed on top of one another E1x and E1, E2x. Sorry, E1z and E2z that I would then have to add together. Now, with the geometry here, you can work out a couple things. You can, one way that we like to do it is the following. We can, so the distance that each charge is away, I'm going to have an R, I'll call it an R plus, which is this distance here. And I call this distance, which is the same distance, magnitude, I'll call that an R minus along that direction, right? Total distance. It should be pointing along that axis. Oh. So, yeah, so ultimately that total field, I guess if we were writing it out in all of its kind of glory, the total net field at point P, we see it's going to have technically two components. We'll have an E Z K plus an E Y J, right? But by symmetry, I can go ahead and just cancel all those out, all the Y components out. And well, I guess a summation along each of those directions. And I'm only going to be left with the components adding up along the Z direction. And they're gonna add together because it's the E1, E1Z, it will add together. Well, yeah, so E1 and E2. So basically, yeah, I guess you can kind of set it so like E plus or E1, so basically EP is going to be equal to E1 or E plus, I guess. We use that E plus. And E plus is going to be, so E plus plus E minus because they're in the same direction. Now E plus, you can look at it using Coulomb's law, E plus is going to be equal to K sub E, Q plus divided by R plus squared. And E minus basically is the same thing, K sub E, Q minus, so the magnitude of Q minus divided by R minus squared. So that's what I'll be adding together, and ultimately you can see by symmetry what we'll see is that the magnitudes are equal. So we can I didn't factor them out, but I still need to kind of go through and work out the geometry on these. So it's a couple things we can say. This distance here, r plus, so we have a right triangle here where one leg is a and one leg is y. So from the Pythagorean theorem, we could work out that, you know what, I'm going to renumber these things so that you can kind of see the symmetry and how I'm thinking about it. I'm going to call this 3a and 3b because there's going to be some things that are going to be very similar between the two charges. So here I'll make this 4a and 4b. So like r plus by symmetry, by Pythagorean theorem, is equal to well, the magnitude is equal to the magnitude of r minus, which is going to be a squared plus y squared, the square root of that. So we could just call that r. So I'll just write that as one equation. Now, I think I also use something here that we could also write r plus as a vector quantity, right? Because I'm at the field point, and I get to the field point two ways. I can go directly from the place where the charge is to the field point, or I can go along the negative a direction and then along the positive y direction. So if I write r as a vector, you know, like you can always, you know, it's pointing as a field point. It points from, that is the field vector. It points from the charge to the point where you want to find the field. So it's actually a vector that's pointing like that. So I could bring it down and represent it, you know, independently mathematically by drawing it from the origin. So you want to also realize that in terms of a vector, this is the magnitude, but in terms of the vector, r plus vector is equal to yj minus a k hat. So yj hat minus a k hat. We talked about that last semester? Yeah, when we defined two-dimensional vectors. The other thing that I want to evoke is the thing from mathematics, like the definition of a unit vector in general, right? In general, a unit vector, so from calculus, remember, calculus, was it 2 or calculus 3? I can't remember. But anyway, a unit vector is defined, I mean, you don't even need, you know, you just take it directly from the definition, right? A vector is defined as a magnitude times a unit vector, right? So therefore, and let me just write this magnitude and some arbitrary magnitude as r, right? Where r is could represent the, you know, distance of that vector. So therefore, you know that a unit vector is defined as the vector divided by the magnitude. So if my magnitude is this thing, the square root of a squared over y squared, the square root of a squared plus y squared, and the vector that I represent is this thing, then I could plug 4 and 5 into 7 and write the unit vector in terms of the vector r and its magnitude. And that is that, in general, the unit vector is, so basically r plus vector or unit vector is equal to yj minus a k hat divided by r, which is, well, ultimately we'll see that r, did I do it that way? Yeah. I guess I could put in the magnitude, or I could just put in, I'm just going to do it, stick to what I have in my notes, r. Oh, I see. That's what the graphs comes from. Okay, yeah, gotcha. Sorry. Old notes. Should we do that? I got it. Yeah, that's why I was doing that. That's why. So I didn't quite finish this thing. This is a vector equation here. Let's see why I was doing that. So here, check this out. So this is the vector equation, which is the superposition of the fields at point P. These guys here, 3A and 3B, are the magnitudes of those vectors. But if I write those vectors appropriately, I have to write them as a magnitude and the unit vector. All right, so I'm going to, equation 9 is going to be the more explicit version of this equation. So from equation 2, this becomes the field at point P. It's got to be equal to the contribution of E plus, which is the magnitude of E plus, times its unit vector, plus the magnitude of E minus times its unit vector. But now I have all the unit vectors, right? So like this unit vector here is, yeah. So this is R plus, but let me write that as 8A. So 8B is R hat minus is equal to, now again, this is R minus, so I could get to the field point from the negative charge two ways. Go directly along a plus R, R, or I can go along the negative direction, sorry, the negative direction of negative A, and then along the positive direction of Y. So in this case, it's a negative, a negative times a negative. So R negative is going to actually be equal to Yj plus A K hat divided by R, the magnitude. Yeah. So again, I'm running out of space here, but I want to keep this down here to keep the symmetry. So 8B is R hat negative is equal to Yj hat plus, this is a minus times a minus, A times K hat, all of that divided by R. So I have the magnitudes of E and plus and E negative. I have the unit vectors E plus E negative. And now I'm going to plug basically equation 3 and 8 into equation 9. So 3 and 8 into 9. So that's going to give me, let's do this in a few steps. I've skipped a bunch of steps in my notes, but I want to do that here. One, because I haven't done it in a while, I don't make any mistakes. And two, because I want you to see it, be more transparent. Now, you're probably going to see this worked out in a book. I mean, all the books do this. It's the standard thing you do. But they might not do it in as much detail. And the reason I'm doing it in so much detail is because I'm using this as an analogy to go to the continuous charge distribution where we're going to have to integrate. And because basically we did this problem already, right? We did the problem a few days ago and I had, 2 charges or 3 charges, whatever, we did it. And I didn't do all this kind of mathematical stuff, right? You don't really have to do all that when you just have discrete charges. but I'm doing it in a very specific way because I'm trying to show the symmetry between going from a discrete problem to a continuous problem. And so the mathematics gets necessary when you have a continuous charge distribution. It's not necessary to do it for discrete, but you can do it. And the most obvious thing to do it with, based on what I'm ultimately trying to teach you with, is a line of charge, is to set it up so that I have a discrete charge distribution, a dipole. Remember when we did it before, I set it up so that the electric field I was trying to find was actually at the origin, and I put the charges out in the other space. Here I flipped it around for a very specific reason. The specific reason of using mathematical symmetry to make the integral problem easier, and also to see that you can actually set up discrete charge distributions that way if you wanted to be able to kind of work through all these mathematical details and redefining these things in a way that is, again, as I said, not necessary for discrete charge distributions, but very necessary for working out continuous charge distributions, but doing it for something that is a bit more familiar first. So I hope a lot of that made sense. I mean, technically, this is actually an easier problem than the one we did before, because the one I did for you last week, the charges weren't the same value, and they weren't placed symmetrically from the origin. One was at 3, 3, one was at 2, 3, or something like that, you know. And we used the vector analysis. We're still using vector analysis here, but again, just doing it in a way that is a bit more symmetric and in anticipation of what's to come. It also illustrates another thing, is that when you're superimposing mathematics onto a physical situation, again, the mathematics is just a matter of perspective. You know, we generally put origins in places that makes it easier for us to figure out the quantity we're talking, you know, we want the quantity we're trying to determine. We could put the axis on the moon every time, right? And then we'd have to make a translation from the moon to wherever we are. So the fact that when I did this problem before, I made the field point at the origin and put the charges out, this time I'm flipping it around, you know, I can do whatever I want with the mathematics. Mathematics is a language, but it's also there for us to use at our disposal in the way that we need to use it. So it's not, you know, there's nothing that dictates that I had to place the field point at the origin like I did. I just did it that way that time because it was easier to point out for you the things I wanted to point out. Now, if I did that for an integral problem, it would make it actually much more complex. So I'm now switching this around for the dipole, again, in anticipation of where we want to go, and just to show you that, you know, math is that way, right? You manipulate it for whatever you need, whenever you need, for whatever you want to do, as long as you're following the rules. Right? You can do that. All right, so hopefully you're kind of caught up and kind of making sense. So now I'm going to take equation 3 and equation 8 and plug it into equation 9. And if I do that, I can now write the electric field at field point P in the following fashion. I have the magnitude of E plus its times its unit vector. The magnitude is K sub B Q plus over the magnitude of the distance away, which I'm going to call R plus squared, times the unit vector, but that unit vector is this thing. It's, you know, Y J minus A K hat, Y J hat minus A K hat over the magnitude of R plus. And I'm going to add to that the second term, which is the magnitude of the field due to the negative charge. And since the charge is a dipole, it basically is the same magnitude. I'm going to Actually, you know what? Well, I'll keep it Q minus, whatever. They're the same magnitude, but for now, I just keep it Q minus. And then R minus squared times that unit vector, which is y j hat plus a k hat over the magnitude R minus. Now, yeah. Is everybody with me still? Hopefully. Now I can do some things. What I want to do, I want to say that, so yeah, we can, so R plus equals R minus equals R. I think I did that before. But also, 11b, Q plus equals Q minus just equals Q. It's a dipole, so the magnitudes are the same. So if I put those in, I don't want to skip steps. I don't know. Sure, why not? I'll just write it all out. So put all that stuff in, so you have in your notes. I said I wouldn't skip any steps. So we have K sub B, Q over R squared times Y J minus A K hat, J, it's J hat, not just J, times R plus K sub B Q over R squared times Y J plus A K hat over R minus. Now or R. So yeah, cool. Okay. So now I can factor out stuff and multiply. So first of all, factoring out an R squared and then R from each term, that's going to make it an R cubed in the denominator. And then in the numerator, I'm factoring out a K sub B over Q. So that would be, oh, it's going to give me, so the field at point P equals K sub B Q over R cubed. And in brackets, let's put it in brackets, I'll have all these are going to be four terms. Y J hat minus A K hat plus Y J hat plus A K hat. Is that right? I made a mistake somewhere. Where did I make the mistake? Oh, the mistake is right here. Yeah, my bad. That's a very careless mistake. It's a careless mistake. So I was so focused on making sure I didn't miss the sign on that term. It's a minus and a minus, which makes that plus. I'm actually going along the y component in the negative direction, right? I mean, that's kind of maybe a funky way of thinking about it. You can just see it here. The y component for E plus is positive, but the y component for E negative is negative, right? So sure, one way to think about that is moving along these two vectors, but I'm going along the negative A in the negative direction, but then I'm going along, you know, the Y in the negative direction, not the positive direction. If I were to take this vector and project, because basically what you're doing is you're projecting this vector, which points from the, yeah, whatever. I don't know, it's kind of hard to maybe see it there, but you can certainly see it by looking at the E field component of, you know, of E to Z. Yeah, it's got the Y component pointing along the negative direction. So the point is that this thing here has got to be negative. That's negative. So when I take that and put that over here, there's a negative sign inside here because the J itself, basically the unit vector is negative. So that's going to make this negative here. And this guy here will be negative right here. I missed a minus sign. But now, that makes sense. Because by symmetry, when we looked at it, we said the negative components have to cancel out of the electric field, because we clearly see that they have to because they're pointing opposite directions. So you have to make the mathematics work out to say that. So here, that Y cancels that Y. And I'm going to ultimately have, oh, but that doesn't cancel either. What did I do? Did I just mess up everything? I did, didn't I? So I guess I missed this minus sign too. I'm so sorry. I didn't look at this before I did this lecture. So I said a minus and a minus. Yeah, okay. So that is the same minus sign. So yeah, so my bad on that. I think I screwed that up. It's not, so you could think of the Z component as pointing along the negative direction as well. Yeah, I think I overthought it. I said minus and minus, but it's just, you're moving along that distance in the negative direction and moving along that distance in the negative direction because it's pointing in the opposite direction. So both of these have to be minus. Yeah, I didn't have that very clearly written there. Sorry, I'm sorry. I hope that didn't screw you up. Probably did. So even that's negative as well. Yeah. I mean, another way to think about this is that, let me go ahead and fix this. So this is going to be negative over here. And that's also negative. Another way to think about this, which I guess I should have, whatever. So I was focusing on the R's, right? And projecting those to the origin. But really what we're adding is the E's. So this E, if I project it back to the origin, you see that it's going to have one positive component and one negative component. I mean, you can see it here. There's a positive component, EY, and then the negative component. That has to be consistent with what I showed. Where is it? Well, here, right? It has one positive component along the Y direction and one negative component along the Z direction. But this guy, it's pointing back in that direction. So if I project over to the origin, both of its components have to be negative. It's actually obvious from this as well, like the y component is pointing along the negative direction and the z component is pointing along the negative direction. So both of those have to be negative. Yeah. So yeah, that's it. I mean, I don't know. I didn't, yeah. So in the end, I'm gonna have these two components cancel and these two components add. And so you can see that the resultant is going to be in the positive and negative. And that's what I said initially, that these two components, I was kind of focusing on the magnitude. So there's two ways you approach it, kind of an intuitive point of view, which is what the schematic is about, but then you have to prove it mathematically. So you can see my weakness is always making sure that my math is consistent with the intuition. But it's definitely clear that from these two charges, the way I've set up the axis, the resultant has to be along the negative z direction. So if you're working out your mathematics and that doesn't work out, then you did something wrong, which is, you know, so I've caught that. So ultimately, and if by symmetry, the magnitudes of these two components is the same. So this resultant has got to be twice the magnitude of an individual one. And I'm going to get that 2 out of that, right? Minus a k hat minus a k hat is minus 2 a k hat, right? And the magnitude then of each component, each individual component is k q, you know, over r squared. Times a really, right? And so basically that works out to match your intuition. So let's finish up the problem and see what we get. So if I then add those two up, realizing it's, and also you see that the vector analysis gives you the right direction of the field too, negative. So the negative sign is going to pop out of that. Where should I do this? Maybe I could do it here. So I add that stuff up and I'm going to get so I'm going to get, the resultant is a minus 2a well, I have the k sub b q over r cubed, and then there's a minus 2a that comes out of that, and all of that's in the k direction. So kind of rewriting that, I get a minus 2 k sub b q over r cubed times k hat is the resultant field of that dipole at this point. Now, sometimes this is written as, let me define something called a dipole moment. Dipole moment. Oftentimes, we treat a dipole as kind of a connected, unified thing. That is, if you think of these two charges as connected by like a rigid rod, rigid massless rod, they're connected, right? So they can rotate, maybe pivoted at the origin. So if, for example, if I place an electric field on this thing, maybe this dipole, since we, you know, this kind of mimics what happens biologically in systems. You know, you can have charges that are kind of connected, and if you pivot them at the center, they might be able to rotate like it's a unified body or a unified object. And so we can define something called a dipole moment, which is essentially equal to um, the magnitude of an individual charge. And it's related to the magnitude of the charges and the distance between the charges. So let's define that. First of all, any questions about this result here? This is the result of the electric field of point P away from the center of the charge. Actually, you know what? I'm going to leave that. I'm going to leave that. We'll get to dipole moment later. I just want to leave this and go directly to now doing the problem of a continuous charge distribution. Yeah. We'll do a dipole moment at the very end. But any questions about that? Questions, problems, troubles, gripes. All right. Yeah. So finally, we get the integration of electric field. Okay. Now what we are going to do is do the same problem, but for a different charge distribution. It's going to be a charge distribution where we assume a finite, is it finite? I have a finite here. Yeah, a line of charge that is centered at the origin and along, basically distributed along the z-axis. So one way to think of a line of charge is that it's kind of a similar problem as this. What if I had several charges? We'll make them the same magnitude, okay? And if I took several point charges, same magnitude and same polarity, point charge, obviously the same magnitude. Well, it doesn't have to be, I guess. And I took them and I lined them up like that. Could be electrons, could be protons, whatever. I lined up a series of point charges. And just to stay with my notes, I'm going to change this from A to L. Well, and I wanted to find the electric field at point P. Well, basically, I would have to do what I just did, but as opposed to doing it with two terms, I'm going to have all the individual terms of the charges that I have set up here. Okay. And also, unlike the dipole, basically the electric field is always going to be pointing away from the charges. So, for example, you're not going to have something pointing toward it. Like if I took, like let's go with symmetry. Let's say that I took now the charge that's at L plus L and the charge that's at minus L. Then this charge, so this picture is going to look the same, but this picture will look different in the sense that now the electric field is pointing away from that charge there, like so. So now I still have symmetry, but my symmetry has shifted. That is, it's the z-axis that actually cancels and my summation is going to be along the y-axis. So I'm going to have basically a field point for this vector E1. I'll still have, you know, E1y and E1z. But now this guy, I'm going to have, you know, E2, if you will call that 2, then this guy is going to be, so this is E2, all right? Then this is going to have an E2 there, Y, but over here, I'm going to have an E2Z, and it's going to be the E2Zs that cancel out, and the Y-axis will add up. But the thing so these go out. But the thing is, I don't just have two charges. I have all these other charges that are going to do the same thing. So like this charge is going to have a vector that maybe points like that, and then, you know, this one is going like that. All the Z-axis, Z components are going to cancel out, and all the Y components are going to add up. Does everyone understand that? Well, I don't actually have point charges. What I have is a continuous line of charge. Let me draw this, getting kind of messy. Let me draw that. But the symmetry and the physics is the same. What I mean is, so consider a continuous charge distribution. Continuous line of charge. Now we could make it an infinite line, but in this case, just to be consistent with the symmetry, I'm going to make it a finite line. Actually, an infinite line is a little bit easier. Then we can use something called Gauss. We'll do Gauss's law next time. We have to get this first. Can't really appreciate Gauss's law until you can understand how to do Coulomb's law with these different distributions. So I won't mention Coulomb's law yet, Gauss's law yet. So let's stick with what we're doing. So we have the Z-axis, we have the X-axis, we have the Y-axis. So I'm just going to go and redo this distribution thing. So here I have A between these two. I call it L, I think, right? And then the same distance below, down something like this. So So now, when we say an infinite line, remember in physics, we generally deal with three different geometries, either rectangular geometry, cylindrical geometry, or spherical geometry. Or in terms of dimensionality, we can deal with one dimension, which is linear, like a line, two dimensions, which deals with cross-sectional area, and that has to do with how a mass or a charge is distributed over a shape. Or we deal with volume, where we're dealing with a three-dimensional figure, and the mass is, you know, all throughout the volume, and not just over the area. So when we say a continuous line of charge, we're also implying that the symmetry is linear, meaning that this charge is kind of a theoretical scenario where the charge is just distributed over the one-dimensional axis. Like I could think of the charge as a cylinder, which is kind of has linear symmetry, but it's a cylinder, so it has volume, it has area, and so the charge is through over. So basically, the axis just goes through the center. I could set up a cylindrical charge distribution in that way. But when I say a linear charge distribution, I'm implying that basically the charge distribution only has one dimensionality, which is impossible, right? That's a theoretical. It's like but it's kind of like I said with the point charge. Like I start off by lining up point charges. If I'm actually dealing with a point charge, it's a point. Like, like the concept of a point particle, meaning the point particle is infinitely small and doesn't have any shape or dimension, which means that it's really only along one axis or one dimension and doesn't have any existence outside of that one dimension. When we're saying a line of charge, we are considering that theoretical scenario where even though I'm going to draw it with some kind of length, because that's just what I have to do, some type of, you could make it a cylinder or you can make it a square, some rectangular type of symmetry, and draw it so that it's distributed over, over the shape of this thing. Okay, so maybe something like that. And I draw it, that making it look like it has some kind of shape, but it doesn't really have any shape, right? It's really, so I'm going to draw it like that, and I'm going to make, actually it looks a little bit off, make it shorter. I made it too long. And this charge, I'll make it a different color. This is, again, you could think of it like point charge. Basically, it's distributed over this thing. Now, actually, I don't want to put the point charges in. Just understand that this is positive, has a positive charge distribution. So, I like evoking the point charge thing because what we can think of is that we like to talk about a continuous charge in terms of charge density. And the idea, so consider a continuous line of charge. So we want to find the field at a point P, a distance away from the bisector of this, of this continuous charge distribution, but we say that it has linear charge density, and we use the symbol lambda to determine linear charge density. So the idea of charge density is charge per unit. Well, in case of a three-dimensional object, density, as you know, is well, like in terms of mass, is mass per unit volume. But you can also have charge density, charge per unit volume, or charge per unit area, or charge per unit length. Those are the three different geometries that I was alluding to. In this case, since I'm dealing with a line of charge, we can say that in this case, the total length is 2L, but we can define whatever charge is on this thing, whatever charge, total charge Q, that charge is defined as, can be defined in terms of its charge density. So if this has total charge plus Q, then the charge density, lambda, is defined as the charge density, linear charge density. The symbol is lambda, and we define lambda as total charge over the total length, which in this case is 2L. So let's just say like total charge over total length. Well, actually, let's see. It can be total charge over total length. Let's just say charge over length. But if it's a uniform charge distribution, that can be equal to the total charge Q over the total length 2L, or it can be equal to any portion of this charge distribution that I want, because we assume that the charge density is uniform. So uniform charge density is a constant. Implies a constant lambda, in which case any way that I break up this, line of charge, I'm going to have the same amount of charge density, or the charge density would be the same within that. So what we generally will do is break it up into differential charge elements, where the total charge is Q, a differential charge element is dQ, where I'm making these infinitesimally small portions of charge. So a dQ is, like a differential charge element. But my point is that, in evoking the point charges, is that I can think of a differential charge element as similar to a point charge. So that if I want to figure out the electric field at point P due to this total charge distribution Q, linear charge distribution, I can think of it as just adding up all the contributions of the differential charge elements, dQ, at a particular point along that charge distribution, and the contribution that thing is making to point P, which is very similar to thinking about the contribution that a point charge would make at point P, due to the various elements or differential elements along that charge distribution. So this differential charge element, it's going to contribute to the field. It's positive, so it's going to contribute to the field by giving a differential field dE, and that differential field is only due to that charge element dQ. And as I add up all the charge elements, then I'm going to get the total field. So there was a question, someone was talking.
I mean, to visualize the charge, are we visualizing the charge spread across the length of this shape here on the y-axis?
Yeah, this charge Q is distributed over the entire length of that charge distribution. Okay. And we're thinking of it as has only one dimension. So we're defining it in terms of a linear charge density, where at any point, again, the total charge over the total length is equal to lambda. But if I looked at this differential charge element, it's actually distributed over a differential length, dl, or in this case, I'm going to make it dz. So I can say that lambda is equal to the total charge over the total length, or it's also equal to a differential amount of charge dq within a differential length, and that differential length could be dl, but since I've defined it along the z-axis, I'm going to take that differential length as dz. So that the total charge then, this gives me kind of three different equations I could write. That the total charge Q is equal to lambda times the total length, in this case is TL, 2 times L, or the differential charge dQ is equal to that same charge density because it's a constant times dz. So it's a way, charge density is a way of It becomes a mathematical tool. We do the same thing with mass density. It's a way of kind of using, it's a mathematical tool that allows us to write the charge distributed over some geometry in a differential fashion as a differential element.
Quick question, Professor.
Yes.
So, would a good way to actually get the dimensions here be to, I guess, differentiate the formula for the area of this shape, and then based on that, calculate the charge, the differential charge by differentiating the formula for the area of the cylinder?
Yeah, I understand what you're saying. Yeah, I think I got your question. In this case, it's not area because we're dealing with linear charge distribution. So yes, you could do, this is not what we're doing, but you could, right, basically, I think your question is, what is the relationship of the total charge to the differential charge element? And it is the following, that total charge, Q, is equal to the integral of lambda dq. So I would have to write lambda in terms of the differential charge element, dz, which I have done so. So a very easy problem is this. Q then is equal to lambda L, and dq is, oh, sorry, yeah, what? dq is, did I do this right? Sorry, no, my bad. Q is equal to dq from 0 to, well, I guess what we could do is we could do twice, right? We could do from 0 to L and then do that twice. If the charge were distributed over an area, then this would have to be a double integral over area. But in this case, it's linear, so I only have to do it as a single integral. If it were volume, then I would have, you know, a volume charge density, and we use different symbols. For area, we use sigma, and I'll wait till we get to that to do it. For area, we use sigma. For volume, we use rho. For a line, we use lambda. But I think this is the question you're asking. If I wanted to get the total charge, that's right. I could integrate from 0 to L, do it twice, and that would give me the total charge over the thing. But because I define dq as lambda dz, then it becomes this. Q is equal to 2 times the integral from 0 to L of lambda dz. The z comes out of the integral, right? So then Q is equal to 2 times lambda, the integral of 0 to L dz. And voila, like that's a simple integral that just integrates to z. So I have that the total charge Q is equal to 2 lambda, basically 0 to z becomes z, right? And then, so then Q is equal to basically 2L times lambda, which is how I defined the thing in the first place. So it becomes kind of a trivial problem because we already kind of know the answer. I'm telling you that Q is related to lambda in that way, but yeah, technically it's a problem that you could work out. And you know, one thing you might, if you've seen something like this before, like lambda doesn't actually have to be constant. It could be some funky, some funky distribution. It doesn't have to be constant. We're always going to probably use constant because this becomes more of a mathematical problem where you're trying to find Q. We're not trying to find Q. We're trying to find E, which is something a bit more complex. But that is, I think, the question you're asking is what is the relationship between DQ and Q? And yeah, that shows the relationship that once you have the differential element, the functional form of it, you can use it to integrate to figure out what the total charge is on whatever geometry it's distributed over. In this case, it's linear, but a more complex problem would be like what if I had some kind of, like what if it was actually a cylinder, right? A hollow cylinder. And I had, charge distributed over the outside of that cylinder, right? That becomes, so in this case, you could say you could call that charge distribution sigma. And, you know, it's basically, it becomes a double integral where I could figure out the total charge over that thing. Or what if it was a solid cylinder and I had charge all throughout the volume of it? Then, you know, I would do it a similar way, but it becomes a more complex problem because it's a triple integral where I have to work out the volume of the thing. So, yeah, that is the relationship between charge density and total charge. Again, we have ways of getting around those complex mathematics with working out the charge, trying to convert it to an integral over a single variable, which I actually will do a similar thing here, even though when I'm trying to find, we're not trying to find the total charge, we're trying to find, because we know it, or at least we know the charge density, so we can know the relationship between that. And we're trying to find the field, so it's something a little bit different. So that was a long answer, but does that answer your question? I think I anticipated your question. Is that what you're asking me?
Yeah, I'm able to make sense of it. Yeah.
Say again?
Yes, I'm able to make better sense of it from what you explained. I was just wondering if, you know, in a real example, we were to expect, you know, physical dimensions that would have to account for in our calculations for the charge, or if we were just going to be able to actually be given the charge density. I didn't know if we're going to have to derive that, or if that was going to be given to us.
I got you. Yeah. Well, basically, you don't really have to. If I give you the charge density, I mean, there's no way to, if you have the charge, you know the charge density by this relationship. So you don't have to integrate it. This is the relation. You see, when I integrate it, I got the same answer.
Right, okay.
Right, like that is the answer. So once you understand the definition between charge density and charge, then yeah, you know it. Now, there is one situation where technically I think it is part of this class. Like, I could give you a charge density that's not constant, such that you would then have to actually work out that calculation, and you're going to get something different than this simple situation. But that's more, I'm not going to do that, because we're trying to find the field. We're not trying to find the charge. And, you know, that's maybe something for a more advanced problem, like a junior or senior level problem, where you don't have a constant charge density. Right now, we're just trying to understand how to work out, you know, basic kind of, a more basic problem is a constant charge, is a uniform charge. So that's the only level of problem we're going to do right now. So if I give you the charge, you could use this relationship to get the charge density. And I could ask you that, I don't know, maybe just to do it, but it's not going to be, it just comes from this definition. You're not going to have to integrate or anything. Or if I give you the charge density, and you know the geometry, the length of the thing, then you can use this formula to get the charge. You wouldn't have to integrate anything there. Now, you're going to focus on any integration for a problem like this, would be focusing on trying to figure out what the field is, not what, you know, charge is or whatever that would be given, or charge density or charge, and then you could use this to work out with the other. Any other questions before I only got 15 minutes? I want to set this up before I let you go. And you can continue working on it. And they're going to have this worked out as examples in any physics book. So you're going to see it, but they might not work it out the same way I'm doing. They might skip steps. So I'm just trying to put all the details in here. But go ahead and read through if we run out of time, which I think we might. So that's the idea of charge density. And with this linear charge, I'll come back to that and revisit that and kind of give you a chart and kind of lay out the different geometries. But this is kind of the beginning introduction. Now, so now that you understand what we're doing, it's a very similar kind of thing. Basically, it's vector analysis. But we're adding up differential charge elements which are infinitesimally small, as opposed to discrete charges that, you know, are not. But when you're integrating, that's all you're doing. You're basically doing the same thing that we just did with the dipole, but you're adding up the contributions of differential elements, which are infinitesimally small. So we can use that same symmetry that we were just using with the dipole to kind of set up the problem to be able to integrate. And the way that I would do that is, again, looking at the symmetry. So if I had a DQ element here, right, and a DQ element down here, that's the same distance below the axis as before, then what's going to happen is I'm going to get some, I'm going to get these cancellations, right? So like over here, I would have a differential element. Like if I had the one down here, it's going to give a contribution like this. Now I'm not going to put in 1 or 2 because DE is just, it's just basically it's just DQ, right? It's like you don't have like DQ represents all the different elements. But if I had a DE here, then I'm going to get some cancellations, right? These guys go, they cancel, they cancel. So what's being added up are the differential element, only the Y components of the differential element. Now here, I have to be a little bit more careful now in the way that I represent that component. I can be smart about it. Now my length here is still R, and I'm not going to write an R plus because each one, like that R is not a constant, it's actually changing. Now before with the dipole moment, those things were constants. But the contribution of, say, the differential element here, it's not the same R as, R is a variable. So the distance is not the same. So what I have to do here is write basically the component that I'm adding up in terms of things that are varying as I move along that guy. And the way that I can be clever about it to do that is I can use geometry to write that component in a way that it as a variable component. That is to say, first of all, the only component I need to be concerned about is the Y component. And that's this guy here, that's DEY. But DEY is equal to DE times the sine, what is it? The sine, well, I have to be careful. If that's theta here, it's cosine actually, isn't it? Yeah, it's cosine. Because that angle is the same as this angle, right? Alternate interior angles for bisecting lines. So that's theta. So this component is the cosine of DE, no matter what perspective. So the thing, dy is equal to DE times the cosine of that angle theta. The other thing that I should be careful about is it's sure that my total length here is L, but I could take any arbitrary, like let me back off this a little. I should have taken a different one because I wanted to show you that we got to be careful. The dipole, the lengths didn't change, but in this case, the Z position of my differential element is a variable, right? Like, let me just take a different one here. I guess one way to do that is I could extend it because I've already got my triangle drawn. So let me just do that. Just extend that up a couple more. Show you what I mean. Put it down. Just keep the symmetry. So right now I'm in here somewhere. That's my differential element. And I'll go ahead and make that total length. Keep that so we can keep the picture in. All right, I'm going to break the symmetry there. Here, down, down. Break it up here. So that when I'm in here, I have to remember that I'm at a position Z that is changing. So that's now a variable. Sure, when I'm at the very end, Z is equal to L, and down here Z is equal to minus L, but Z is a variable. Is a variable. So now my R can be written in terms of that varying Z and this non-varying position Y. Y does not vary. It's still a constant for this particular problem because my point P is not changing. So I think I have everything I need to write down as a setup. I'm going to set this. I want you to work this out at home. And I think you're going to have to use, actually work out this integral. You can look it up in the integral table once we finally get it set up. But I think you can also use trig substitution to work this out. So it'll give you an opportunity to really struggle that out. Yeah, trig substitution is the way you work it out. One way to work it out once you get it set up. So let's go ahead and see if we can set this thing up. Now I'm going to jump forward and use the well, I guess we can just do it the way I wrote here. Yeah. We already know that the z components are going to cancel out. So yeah, so I have all this. So basically, again, the same thing. If we start here, we want to know the electric field at that point. And just erase this for a second. So we could start off the way we did before, that dE, the total field at point P, is equal to dEyi plus dE zk. Now, as opposed to kind of doing the stuff that I did before, where I did the, define the unit vector, that was one way to do it. I'm going to skip that now because I can just use symmetry, and I know that the z component is going to cancel out. I could do it that same way, but do all that stuff. I wanted to show you at least once. That's one way to formally work it out, to understand that mathematically, using that the definition of unit vectors, you can show that it cancels out. Here, now that we've done that, then I'm just going to jump to the fact that the y components are going to add up. Yeah. Now, as I said before, the y component, let's go ahead and number this, dEy is equal to dE times the cosine of theta. I'm going to go ahead and stick that guy in here so that dE at P is equal to dE times the cosine of theta, basically times unit vector I. Now, dE, what is that? Using Coulomb's law, I can just write it down, right? I'll do it here separately first. dE is equal to K sub B. Now, it's basically, we have to use that integral form, right? That integral is dq over r squared. So that ultimately, E is, well, yeah, we'll integrate it. We'll basically, E is equal to the integral of K sub B dq over r squared. But for right now, I'm going to just leave it as dE and stick it in. And cosine theta, what is that? That's going to vary because the angle is varying as I go down. But I can write cosine theta in terms of my geometry here. That cosine theta is adjacent over hypotenuse. And the adjacent side of that right triangle is y, which is a constant. But the r is changing because as I move down, that changes. So cosine theta is equal to y, which is constant, over r, which is a variable. So when I put equations 4 and 5 into 3, I now see that my electric field at point P is equal to K sub B dq over r times y, over r squared, times y over r. Yeah. Okay, we're on a roll. I'll finish at least setting this up before you leave. Now, let me go ahead and integrate. If I integrate both sides, then this integrates to just EP, right? Integral of dEP is just EP, the value of the field at that point. But over here, I have to work out the integral. So I have K sub B, none of that stuff. Well, the only thing that's constant is Y, but I'm going to leave it in just for a second. So I have dQ. So basically Y times dQ over R cubed. That's what I have to work out. Now let's put in the other stuff that I figured out. I know that my D, so the Y is a constant. It's going to come out of the integration. And I also have my, I can put in my dQ is equal to lambda dz. So equation 8. So EP is equal to the K sub B, taking out the Y. I'm going to go ahead and write the key. Well, yeah. I'll keep it as K sub B right now. So K sub B, Q, and the dQ now is going to be lambda dz over R cubed. But let me just write up, let me make this equation 9. Let me just write up here that R cubed, R is going to be the square root of, still the same thing we did before. It's the square root of y squared plus z squared. R is equal to, and that's the same thing as y squared plus z squared to the 1/2, right? Because taking the square root of something is the same thing as, raising it to the 1/2 power. So now then, if I substitute equation 8 into equation 9, that's where you get that classic 3/2 power thing. That's where it comes from. And also, I'm going to go ahead and write K sub B as 1 over 4 pi epsilon naught. And start to look more like what you're probably going to see it written as in your physics book or in some wherever. So I'm going to have Q, and I'm going to fract out the lambda as well. I have Q lambda over 4 pi epsilon naught, the integral of dz over y squared plus z squared to the 3/2 power. And I left out a z somewhere, didn't I? Where's the z? Did I miss a z? Oh no, that's the z component, which I didn't. Yeah, sorry. No. If I had done the y component, I would have had a z there. And but no, the y. Sorry, if I had done the z component, that would have been very similar, but there would have been a z in the numerator. But I didn't do that because I just canceled out in the beginning. So this is good. This is it. So this is the integral that we have to work out, and we have to go from you can go from minus L to L. So in this case, I guess you could do 2 and do half. You could do that. You could go from 0 to L and multiply it by 2. Or you could just go from minus L to L. Either way, you'll get the right answer in this case. I think I'm just going to have it go from minus L to L. So what I'm going to suggest is time to go. Yes, it is. So time to go, but I'm going to let you. So basically, that's what's set up. That's what you have to do to work out like Coulomb's law for it. That's one version. Now, to do this integral, you could actually look at both in an integral table, or I'm going to at least work it out once. You could do a trig substitution. So I'm going to go through that, and maybe you could practice that if you want, or just, you don't have to, but you can look it up in the book if you want. But if you do something like z is equal to tangent theta. Z is equal to y, and you get it directly from this thing, right? Tangent theta is equal to opposite over adjacent, z over y. So z is equal to y tangent theta, right? So then taking the derivative of that, dz, the derivative of tangent is secant squared. So that's going to be y secant squared theta, and you also have the d theta there. So you could use that trig substitution to actually work out the mathematics of the integral. Or you could find that specific integral in an integral table, get the answer, and then translate it. Either way you want. I'll work it out at least once to show you, because this is an integral that kind of comes over and over in physics. So if you understand it very well once, then you're not intimidated by it when you see it in the future. Even if you do decide to look it up in an integral table. But it's pretty straightforward trig substitution to work out, so we can knock it out in a few steps and then come back and then we'll look at the final solution. So I'm going to start there on Wednesday. We'll finish that. We'll start right there, work on the mathematics, finish that. And then we'll do a couple other problems, which won't take so long, because part of this is I was showing you how to set it up. But we'll do like a disc, a ring, things like that. Get pretty, once we kind of, we'll do a few basic problems that you'll see for problems like these. All right, so we did a lot today, but that pretty